Say you have an unfair coin. We want to estimate the probability of heads, P. Now, if your immediate instinct is just to start flipping the coin, that would be right? So the idea here is we just flip the coin, mess around with it a bit until it lands on heads. Now, the first time we do this experiment, it'll take 3 throws. The second time it will take 5 throws, and the third time it will take 4 throws. We could do this experiment, 100 times, and our probability would be much more accurate. But for this example, we're just going to do 3, and you'll see quickly this is easily generalizable. Now, if we let P be the probability of heads, and we want to find the maximum likelihood estimate, P hat for P. Now, if we let x1, x sub 2, x sub 3 be identically independently distributed geometric random variables with success probability P, right? Then already maybe you'll see where I'm taking this. So I'm just going to let my likelihood function be this guy here, right? Where I'm just wondering what's the probability that on my first experiment, it took 3 throws. On my second experiment, it took 5 throws before my first success. And on my third experiment, it took 4 throws, right? And then our second equality in the middle just comes from what the geometric distribution is. So our 1 minus p squared and our 1 minus p to the power of 4 and our 1 minus p to the power of 3 is the number of failures before our success, which in this case happens at toss 3, 5, and 4. Now, on the most right-hand side, all I'm doing is combining our terms. And then it's just about finding the maximum of our likelihood function. So here I take the derivative of our function. I'm just using the product rule here in our first equality, and I set that equal to 0. And then after eliminating, 3p squared from both sides and 1 minus p to the power of 8 from both sides, we're going to get 1 minus p equals 3p. And that gives us p hat is 1/4. And then we're done.